Welcome, everyone. The live stream will begin momentarily. Okay, right now we're just sending out some notifications so that people are aware. We do have an open chat. The live chat is open, so you can try that out. All right, looks like we've built up a nice little crowd. I see Pam is here. All right, welcome, welcome. This video will be available and it will be recorded, and hopefully I don't screw it up so we can recycle this material. But if we don't cover everything, we can just redo it. We can do another one next week as well. So we don't have to cover every single thing tonight, but I do want to touch on some important things. There's a lot of chapter 6 stuff. I've always said chapter 6 is kind of the meat and potatoes of the course, and I do want to spend some time making sure that we're all clear on chapter 6 stuff, normal distributions and finding the probability of certain things. And it turns out that some of our problems on the practice final are, have video support for it as well, so that can be very helpful. So let's dig in. Let's just see what's going on. Make sure everything is set up, and let's just access the practice final and take a look at some of those problems and kind of just walk you through some of the strategies that I would suggest you do while the practice final is live. Because once it closes out, you cannot access it anymore. So right now it's like a gold mine. You can access it now. Even if you're not ready to access it, I would strongly suggest just accessing it now and actually try to print it out at some point. You know, take it as if it was a real test, and then review the answers by printing it out, and then you can have that as well as a study guide for any like last minute preparations or anything like that. That's a strategy that's fair game, and you know, it could be pretty useful. So what we'll do is access the practice final updated, and this does not count for your grade, all right? So there's 600 minutes, all right? It's just a time that I put in so that you don't have to worry about time. All right, so what is that, 10 hours? Then you get multiple attempts, and you can you just hit start. Just do 30 questions, so 30, each question's a pop. And this is just how the format of the actual final will be. You'll see a screen like this, but instead of practice, it will be final exam, and you will start it just like that. All right, so yeah, I'm surprised that it doesn't show from what section this problem is from. I think in the review it does. So like after you've done the problem, you submit the test by this blue button, and when you're reviewing, it will actually show the section that the particular problem came from. All right. So find the area of the shaded region. The graph depicts the standard normal distribution with a mean of 0 and a standard deviation of 1. Okay, so that's what they mean by standard normal distribution. Now, if you don't have any technology, like back in the day, you know, back in like the early 90s and 80s and 70s, they used tables. And so that's why they're still here. It's kind of just a novelty thing of stats. And if your calculator went down, you can't find it, it broke, you can still get the answer right by using the table. All right? And the table is set up exactly for this kind of problem. Now, basically, based on this problem, all you're trying to do is find the area of the shaded region, which happens to be the probability of getting a score of 0.79 or lower. So these are all scores. 0 is the mean, right smack in the middle, and this z-score is at 0.79. So we already know that the entire normal distribution is 100%. We're a little bit more than half, because at half is 0, And so we can already guess, like if I had to do a wild guess, I can say, hey, it's about 55% maybe. Well, we actually want to know the exact amount to the nearest 4 decimal places. And there is a way to do this. We can use our calculator or we can use a table. All right. Now, if we wanted to use the table, we'd have to find, let's see what the tables look like real quick. Well, here it has the negative z-scores. So if our area is to the left of 0, we get to use these values. All right. It doesn't look like we're to the left of 0 because our z-score is positive. It's greater than 0. So let's look at the second page of our table. All right. Now the second page deals with z-scores that are to the left, to the right of 0, positive z-scores. So all the areas, these are probabilities, aka also it was shown that the area equates to the probability. So I already know that all of these are going to be more than 50%. In fact, if you have a z-score of 0, the area, the cumulative area under the curve will be exactly 50%. Okay, and 0.01, if your z-score is 0.01, that's how you would read it, we're already at 50.4%. Now, our z-score was given to be 0.79, so I have to go to the 7/10 and 9/100. So it's actually going to be this row and the very last column, 0.7852. And that should be my answer. In fact, it is looking for the answer that corresponds to the table. The calculator will give us an answer even more precise than this, so that when we round it, we will get this. So there is a level of tolerance, but 4 places out is really good. Let's actually do the same problem on our calculator for a second, though. Okay, so how would we go about doing something like this on the calculator? How would we find the cumulative area of the standard or normal distribution? Again, this is actually what I will always refer to as a normal CDF type of problem. The normal cumulative density function will give us the answer. And so in order to do this, we're going to go to the distribute function button. So second, distribute. And the second choice is normal CDF. We do not use the first choice. It's a trap. It's actually the probability density function that actually gives you the actual curve if we were to graph it, but we don't need that. It's number 2 is the one. That's the go-to one. Number 2, normal CDF. And normal CDF will accept 4 parameters, 4 inputs. Okay, so once you select it, you will be prompted for the 4 inputs. It needs a lower bound, an upper bound, the mean, and the standard deviation. Now, the mean and standard deviation is going to be 0 and 1 because we're talking about a standard normal distribution. And there is no lower bound. So we get to put in some negative number, some large or very small negative number in our case. And then the upper bound is actually going to be 0.79. So we're just going to put in 0.79 and everything else is good. And then just hit enter. And there's what we get. So if you don't have on Stat Wizard, it's not going to prompt you. You're just going to get this, and you need to know what are the 4, the order of the 4 things you have to put in. So it's the lower bound, upper bound, mean, median. Hit enter, and we got 0.78523, which rounds to 0.7852. Now, if I go back to mode for a second, and I turn off the Stat Wizard, like maybe your calculator just doesn't have it. Now when I choose second distribute and choose number 2, normal CDF, they don't prompt me. You have to know what goes in there. So it's nice when they prompt you, and that's what Stat Wizard does. Because sometimes it's just, you can easily forget which one goes in and which one doesn't. So I'm going to put back on Stat Wizard, go into mode. If you have Stat Wizard on, I might as well put it on. And also Stat Diagnostics, you would want to turn that on as well. So when we do a chapter 10 problem, you'll see why you would want to turn that one on as well. Okay, so I've turned it on. Now second quit, and we've done that problem. All right. Here's another kind of question. It says, assume that a randomly selected subject is given a bone density test. Those test scores are normally distributed with a mean of 0 and a standard deviation of 1. So that is the standard normal distribution. Draw a graph and find the probability of a bone density test score greater than 0.39. And if you look at all of the different pictures, it looks like D represents that. And now they actually want us to calculate what is that probability of getting a score that is 0.39 or higher. And so for this, it's a normal CDF problem again. Whenever you're trying to find the area or probability or proportion of a normal distribution, it's normal CDF. You have to simply put in your lower bound and your upper bound. Now, there is no upper bound, so we do have to put in an extremely large number. Actually, the truth is, in a standard normal distribution, 10, the number 10 is actually a pretty large number. There's no difference between 10 and 1,000 and a billion in a standard normal distribution, because already after 3 deviations, that's already 99% of the entire distribution is accounted for. And once you go past 3 deviations, you're more than 99% covering every data point in that standard normal distribution. So what we would do is go into second distribute, number 2, normal CDF. Our lower bound this time is 0.39. Our upper bound needs to be some large number. I'll put in 100,000. We're dealing with a mean and deviation of 0 and 1. There it is. Hit enter, and there it is. It looks like we're getting 3482. Now, it was actually 3482.6, so I'm going to round it off to 3483. Okay. Same type of problem. Let's see. Assume that a randomly selected subject is given a bone density test. The scores are distributed with a mean of 0 and deviation 1. Find the probability that a given score is between negative 2.05 and 3.82. All right. So one is negative and one is positive. Very far out. 3.82. I remember every score does represent a deviation. So we're 3.82 deviations away from the mean in the standard normal distribution. The mean is 0. So the area, the probability is almost going to be like 99%. I mean, it's a lot. Like most scores will be between negative 2 and 3.8. So I'm going to go with, if I look at all of them, B is the one that represents the situation the best. A just looks weird. I don't know what's going on with A. For some reason, A just looks like the entire thing. And then this one almost looks tempting, but the only problem is they said from negative 2.05, between negative 2.5, 2.505, and 3.82. So for that reason, we're going to go with B. And how would we solve this? We would simply use a calculator. Our lower bound would be negative 2.05, and our upper bound would be 3.82. So I'm just going to go with a second entry to recall the last function, the last input that I did. I'm going to delete out what I have here. I'm just going to put in negative 2. What did we say that was? It was negative 2.05, and then 3.98 or 82? Okay. And because it's standard normal, you don't even have to put in the mean zero. It's assumed to be true. 0.97975. So my answer will be 0.9798. I'll round that 7 off to the 8. It's closer to 9798 than it is 9797. So that I'm going to put in 0.9798. All right, so right now, nothing too scary or weird right now. Everything is pretty straightforward. All right, so this is an interesting question, and this reminds me not only of 6.1 question, this is a 6.2 question. This time we're dealing with a standard normal distribution, but it's actually not standardized. It's just a normal distribution, but the mean is not 0 and the deviation is not 1. The mean is 100 and the standard deviation is 15. All right, which is an IQ test. IQ scores, the mean is 100, standard deviation is 15. So if you have a score of 124, then you're almost 2 deviations ahead of everyone else. Find the area of the shaded region. The graph to the right depicts IQ scores of adults, and those scores are normally distributed with a mean of 100 and standard deviation of 15. So we know 106 is just more than 50% right away. And then 124. So we need to get this portion. We need to know what is that proportion of the entire distribution. We know the whole thing is one whole. And so this would be some fraction of that, less than 1, obviously. The way to do this is, again, normal CDF. This time we'll put in our mean as 100 and our standard deviation of 15. Now, there's actually another way to go about solving this, and that's with using the tables. But in order to do that, because the tables only give us for the standard normal, we would have to convert the scores to the z-scores. We have to subtract it from the mean and divide by the deviation to figure out what z-score would this correspond to. Probably like 0.03, something a little bit more than 0, because remember 100 is in the middle. And 124 will probably correspond to about 1.4 or 1.5. And then once we knew those numbers, once we standardized those numbers, we could easily use the tables to figure it out. But why go through all that when we could just do it this way? We'll put in 106, comma, 124, comma, the mean is 100, and our standard deviation is 15. Close it off, hit enter, and we got 0.2898. So about 29% of all of that people who took the test, about 30%, that's the upper, that's 30% of people scored in there. Okay? So 0.2898 is what we would do, rounding it off to 4 places. All right, let's look at a couple more. Now we're honestly not going to go through every single question in order. It would take a long time, several hours. I will hop around once the problems start to get a little redundant. I'll hop around, but it was good for us to warm up because now we're thinking properly about this situation. So it says the lengths of pregnancies are normally distributed with a mean of 268 days and a standard deviation of 15. Find the probability of a pregnancy lasting 307 days or longer. And then B, if the length of the pregnancy is in the lowest 3%, then the baby is a premature. Find the length that separates premature babies from those who are not premature. And that's a good question. Now, because they don't give us a picture or an image, that's the first thing we should do is create our own image. So that's what I'm going to do. I'm going to pull up some notes here, and let's write this out. So the lengths of pregnancies are normally distributed with a mean of 268 days. And I'm assuming that that's accurate. And we're also given, and I'll just write that the mean of pregnancies, and I'm assuming this is like 9 months, right? Very close to 9 months. If you did the math on that, we divided it by, well, we could divide it, we could divide it by 7 first, and then divide by 4. We figure out how many weeks, and then divide the number of weeks by 4 to figure out how many months this is about. But they didn't ask us to do that. The mean is 268. And then the standard deviation of this sample is, again, 15. Now, find the probability of a pregnancy lasting 307 days or longer. So 307, I'm just going to put a bar down here just so I can have a point of reference. Each bar is a deviation from the mean. So again, 2 bars is already 30 deviations. So that actually would put us at 298. And if I were to subtract 30 from this, that'd put us at 238. Now, they want us to figure out 268 is the mean, but we want to know from 307 days or longer. So for 307, I will estimate that to be about here. And what I'll do is highlight that, and I'll put 307 right there. And it's 307 or longer. I wonder, does that have a name for pregnancies lasting longer than a certain? They say there's a name for babies where they were born earlier than the mean, much earlier. But what is it called if they're born later? And now what we need to do is figure out this proportion from 307 days or more. And basically what this is since we're trying to find this proportion, it's a normal CDF problem. It's normal CDF. Our lower bound is 307. Our upper bound is some large number, and I'm going to put in 1e to the 9, which is scientific notation for 1 times 10 to the 9, which is a billion. My mean has to go in, and my standard deviation has to go in. And that would give me the proportion of that region. All right, and let's go on and put that all into the calculator. So I'm going to do a second entry, and let's just clear out all the things in there now. Now let's see, what do we have? We have 307 and then some large number, comma, 1e, and that's the EE to the 9, and then comma, I think we said 268 and 15. All right, So there's our proportion. It's going to be 0.0046 to 4 places, but actually the number after the 6 is another 6, so we get to round it up. 0.0047 is what we got for that. So not many are going to last that long, longer than 307 days. Not many at all, according to our statistics that we just calculated. Okay, that's about, I mean, that's not even, that's, if we even convert this to a percentage, this is less than 0.5%. All right, tiny, very rare. And nowadays we know they don't play that. They will take it out. You will get scheduled for a C-section. They don't want it to go longer than what it's supposed to. Okay. Part B. Babies who are born on or before blank days are considered preemie. So it says if the length of the pregnancy is in the lowest 3%, so that's what we need to do is find the, let's go back to our picture. Now the lowest 3%, we don't know where that is, but we can take a guess. Because this is a normal distribution, and we know half is 50%, and about half that tail is about 16%, right? We could say that this, we could just designate this area, I'll highlight it yellow, as the lowest 3%. Let's make sure we're going for, yep, lowest 3%. Let's just make believe that that is the lowest 3%. Or we could put it in as 0.03, the lowest. The question is now, this is opposite of normal CDF. This time we actually have the proportion, and we don't know the bounds. We don't know this score. We know that the lower bound, we could, it's just some small number, but we need to figure out what is this value that corresponds to the 3%. So because it's the opposite of the normal CDF, we're going to use the inverse norm function, and the inverse norm is when you have the proportion and you need to find the bounds. And the way inverse norm works is you need the area to the left of the bound, and that's exactly what we have here. So we could easily figure this out. I'm going to put an inverse norm, and then I'm going to put in the proportion, which is 0.03. I have to put in the decimal equivalent of the percentage, and then I have to put in the mean and the standard deviation, which is 15. So inverse norm will accept 3 things. That's a big difference between normal CDF and inverse norm. Our inverse norm will accept 3 parameters, and normal CDF will accept 4. So this is where we're going to go back to second distribute, and then under normal CDF is inverse norm, and it's 0.03. Our mean is 268, and our number of days is 15. We are dealing with the area to the left, and it looks like we have a day, 239.78. Now let's see, did they want us to round anything off? It's a find the length. Okay, round to the nearest integer as needed. Well, because we have 239.78, we can just go on and say the nearest integer is the nearest whole number. So I'm going to round it up to 240 days. That is the number that separates the premature babies from the not premature babies. 240 days is the benchmark. So if you're at 240 days, you are in the lowest 3%. Let's put that in there. And so that's how you would do that. All right. Find the critical value, z sub alpha divided by 2. That corresponds to the given confidence level. So we're given, we need to find z sub alpha over 2, and we're given a confidence level of, what did they say, 82%? 81%. Now, the alpha is actually going to be the difference between 181%. So if we do 100% minus 81%, we're going to get the alpha. Now that's 19%. Okay. And what does that mean? Now the confidence levels, that's the innermost 81%. In fact, this is the negative z alpha over 2, and this is the positive z alpha over 2. Because remember, the remaining pieces, the total of the two ends is 19%. So half of this, half of 19% is actually 9.5%. So we have 9.5% in this, and we have 9.5%. And what we need to do is find the z-score that corresponds to the top 95%. So basically, I need to find the z-score that corresponds to the top 0.095%. Now, problem. Inverse norm doesn't give us the z-score when we know the area to the right. We have to know the area to the left in order to do this problem. Well, we could get that pretty easily because the area of the whole thing is 100. So the area to the left is going to be 1 minus 0.095, which is going to be 0.9015. Did I just mess that up? Let me double check that. 1 minus 0.905. Okay, no problem. Okay. Yeah, I mean, it's 90.5 basically. So the area of all of this is 90.5%. That's hard to see. (9.5%) and 90.5%. And we need to find this. And so the way we're going to do it is inverse norm. We know the area. We don't know the bound, the z-score. So here's what we're going to do. We're going to go into second distribute, number 3, inverse norm. We're going to put in 0.905. Everything else is just 0 and 1. Point 1.3105. So 1.31 is good there. .31 is good there. Here we have the brand manager for a brand of toothpaste must plan a campaign designed to increase brand recognition. He wants to determine the percent of adults who have heard of the brand. How many adults must he survey in order to be 95% confident that his estimate is within 5 percentage points of the true population percentage? And then complete parts A through C below. Assume that nothing is known about the percentage of adults who have heard of the brand. And then part B, assume that a recent survey suggests that about 84% of adults have heard of the brand. All right, so this is where the proportion is unknown in part A, and then in part B, the proportion is known. All right. So this reminds me of a chapter 7 problem. And if you remember our lecture video, I actually gave a program that you could use and program your calculator to have this program in it. Did anybody do that? Now, you didn't have to do it, but because there is no calculator function that will be able to do this problem for us, we created our own, and it's fine if you happen to use that. But if you don't use it, then you just have to know the formula. You'd have to know what the formula is. Let's see if we can recall the formula. The number of people sampled, and let's just double check, it's the margin of error. Actually, hold on. Let's hold up. P hat, Q hat, and then divided by E squared or something like that. I think I'm gonna have to check. I'm gonna have to double check this formula and make sure that I have it right. It's either Z alpha squared or not squared. And we know P hat is the proportion. Now, if P hat is unknown, then it's that. And that's just assuming what they're doing there is they're just letting P hat be 0.5. And then 1 minus P hat is Q hat, which is also 0.5. And the 0.5 times the 0.5 makes 0.25. And that's what's happening inside our formula. Now, let's make sure we have the right critical value for this problem. So let's double check that formula And there's several places where we can go to double check our formula. We could just go to our notes for chapter 7. So in the files menu, let's pull up. We can go to chapter outlines. Go to chapter 7 and okay, so the margin of error is this. But if you solve for the margin of error, if you solve for n, you would get that z sub alpha over 2 squared times p hat q hat is e squared. So we're talking about, this is the positive critical value, alpha over 2. And then you're squaring that times p hat q hat. So our formula looked okay. Our formula was really good. Let's go back to our formula. It is important to note that this is the alpha over 2. That goes on without saying that we are dealing with the critical value, alpha over 2. It is the positive side of the tail, of one tail. Let's tail to the right. All right, now let's go back to the problem. They give us the 95% confidence level. So alpha is 5% and alpha over 2 is 2.5%, which means alpha over 2 is 0.025. And we need to get that value that corresponds to 0.025, which is the area to the left, therefore, is 0.9. Let's see if we can get this right. 975, because we're doing 1.00 minus 0.025. And when you line that up, you're getting this. So we need to get that z critical value from inverse norm. That's what we're missing. And then we're going to square it, because that's what the formula wants us to do once we get our value. Now the truth is because this is such a common confidence level, 95%, it should be in your table. It's a very common number to calculate. So we can calculate that out pretty quickly if you have your table handy. If you don't have your table handy, well, just use your calculator and just go to inverse norm. And we're going to put in 0.975. And it's going to be 1.96. Use 1.96. So here we have it. We have n equals 1.96 squared, and then we need the p hat q hat, and then all over the margin of error squared. Now, where do we get the margin of error? Well, it says the estimate is within 5 percentage points. So that's E is 5%. Which is really 0.05. So the number of people that need to be surveyed is 1.96 times p hat q hat. Well, we don't know p and q in part A, so we're going to just put in 0.25 divided by the margin of error, which is 0.05, but we have to square that. And then we round up. That's the thing that you got to remember about this particular problem. And I would suggest checking out my Panopto lecture video on 7.1. I actually go over how to program your calculator to do this kind of problem. So here we go. We do 1.96 squared. I sometimes I do the problem in pieces. I don't put them all in at the same time. I'll do it in pieces. So I'll calculate this first, then I'll just multiply by 0.25, and then I'll just divide it by 0.05 squared, which is 0.0025, but I'll just put in 0.05 and then squared. All right, so we actually got 384 and some change. And it doesn't matter, we can't have a half of a person or a fraction of a person, so we might as well round it up. Say, hey, we need to survey 385 people. Now, in part A, it's because we don't know the percentages, we're going to say, well, you need to survey 385 people. Exactly that amount. No more, no less. Now, for part B, it says that we actually do know that the percent of adults who've heard of it, and therefore the p hat is 0.84. So if we go back into, these are going to be on the big test because I'm spending so much time on this. It's going to be on there. All right. Let's keep going. We got n equals 1.96 squared, and then we're saying that p hat, well, listen, p hat is 84%, which means q is going to be 0.16 because together they make one whole. And then we're going to divide that by 0.05 squared. So now I'm going to use my calculator here. And what I'm going to do is start off with 1.96. Let's clear all this out. 1.96 squared. Then we're going to multiply by 0.84 and then also 0.16. And now I'm going to divide all of that by 0.05 squared. All right. So I got 206.52. That means we need to survey 207 people. You always round to the greatest integer in these kind of survey problems. And then what else is there? Given that the required sample size is relatively small, could he simply survey the adults at the nearest college? Well, the nearest college, you got to keep in mind that one of the requirements is that we're having a random sample. And we're talking about brand manager for brand recognition. So we don't know what kind of campaign certain toothpaste companies have been running at a certain college. So we got to be careful about that, given that it's could he simply survey the adults at the nearest school? So the question is no, but why no? So no is a sample of students at the nearest college is convenience sample, not a simple random sample. No is at the nearest college. It is not. It's a cluster. No it's a stratified sample, and then yes, a sample of students in the nearest college is a simple random sample, so the results should be representative. Well, you know, these again, you can interpret this in a lot of different ways, and that's why sometimes I don't really necessarily like these kind of questions, because when you talk about a college, that is its own unique cluster of population or society. Um, but in the context of this book, we don't really talk about clusters being in a college school. There is, and also when it comes to convenience sampling, there is some convenience for him to simply go to the nearest college. But the truth is a convenient sampling is when you are people are kind of volunteering their time freely. So you're really not doing anything. It's like it's more for polls and stuff like that. And then stratified is when you have a certain population and you are pulling a subset of that. And so for that reason, I'm gonna go with C. Um, but yeah, I mean, it could be almost anything. You know, sometimes you just have to go back and double check what it said there. But what's happening is every college is a strata. And so if we happen to take a simple random sample from that college, then it would work as a stratified sample. So that's one of the reasons why I'm going with it. But I mean, yeah, I mean, you could choose other ones as well, probably, and still be right. So yeah, that was a good question. Let me see. Um, Actually, wait. No, yeah, it's convenience. It's a convenience sample. Um, and here, the giveaway is that, let's go back to the question again. If you simply survey the adults at the nearest college, why the nearest college? There is some convenience in that. And so that's kind of what they mean by convenience sampling, is that it's relatively easy to access. Um, so keep that in mind. Had they said, if they didn't use the word nearest and simply, then it probably would have been stratified. But again, we need a little bit more information though in this type of problem. But the correct answer is A. All right, that was a good question actually. It was a very good question. All right, now this question will not be on there. I will tell you, I'm going to pull this question just because this is more like a kind of like a chapter one type of question. And it was so ambiguous when we were learning about this that I just felt like it wasn't quite fair. They were very tricky questions. And this answer is actually tricky because it turns out that it's not satisfied because the rates for those that develop the polio in the two different groups are not statistically significant. We're going to kind of stay away from those type of questions because those can be misinterpreted pretty easily. And I don't want you to be hung up on any questions like that type. This is a good question. I mean, you have to be able to conduct a hypothesis test um, in stats. I mean, that's just one of the things that you have to go through. So uh, our class is no exception. we we basically have to know how to conduct a hypothesis test. So let's read it. It says a study was conducted to determine the proportion of people who dream in black and white instead of color. And I think it's fascinating that people actually dream in color. I'm like, how could you dream in color? It's amazing. I would like to dream in color. I didn't think you could, but apparently you can. I would love to have some color in my dreams. I don't think I've ever seen color. All right, anyway, all right, listen. A study was conducted to determine the proportion of people who dream in black and white instead of color. Among the 305 people over the age of 55, 60 dream in black and white, and among the 295 people under the age of 25, 12 dream in black and white. Excuse me. Use a 1% significance level to test the claim that the proportion of people over 55 who dream in black and white is greater than the proportion for those under 25. Now, they actually tell us, they say, consider the first sample to be the sample of people over the age of 55, and the second sample to be the sample of people under the age of 25. So, right away, because we're testing the claim of people over 55 dreaming black and white is greater, we're going to go with our choice A. The null hypothesis is that the two proportions are equal. That's what we're going to assume true. And we're going to see if we have enough evidence to reject that null hypothesis and accept the alternative. Now, how did we know to go with A and not all the others? Well, first things first. The null hypothesis has to have equality. They have to be equal. And so we could eliminate half the choices. C, E, and F are eliminated right away. Not in this class. H null will always be some parameter equal to something else. And also, because it says that we're testing a claim that the proportion of people over 55 dreaming in black and white is greater, and P1 is considered the people over 55 who dream in black and white, we have to go with the alternative. P1 is greater than P2. All right. So, yeah. Now, where do we go from here? There's a lot of ways to go. Now, I will show you how to do this how to actually do this using the calculator. But I want to just kind of dig into this and dig into the numbers and just understand what's really happening, what conceptually is really happening. Like a hypothesis test is considered the most powerful statistical test that stats has to offer. It is so powerful that it stands up in the court of law. It can determine someone's life, whether they're guilty or innocent. So when a hypothesis test is carried out, the results can be very conclusive. You cannot refute the results if you get a conclusive evidence to support or reject a claim. So for that reason, we are going to spend a little bit of time on this. Let's look at the numbers. And first, let's dig into, it would probably be nice if we had like a two-way table. But that's fine. We don't have to like create a two-way table or nothing, but I will just pull up a new sheet, and I'm gonna write, well, let's see, we just lost everything. I'm gonna write this one up in our notes so we can kind of analyze what's happening. I'm gonna write down the most important information. Actually, how was I able to do that? All right. 305 people. So we have age, '55 or older, 305, 60, black and white. Okay, and then we have age 25 or younger, 295. Out of the 295, 12 black and white. So let's say we have less than 25, and then we also have an age '55 or greater. There were 295 in this category, 305 in this category. Not much difference between the two populations. This is fine. Okay, granted, the older group, definitely the senior group, so they're like senior and then there's like younger people, but 300 and the difference is 10 people. That's fine. You know, that's not much of a difference. But let's talk about the black and white, though, the people who actually dream in black and white. Now, we have 12 in this group, and we have 60 in this group. Now, 60 is 5 times more than 12. So even though the samples are somewhat similar, there's a little bit more. Obviously, we can expect 1 or 2 more because we do have 10 more people in the larger group. But how is it that we have 5 times more people doing black and white than in the smaller group? So basically what we're trying to figure out is, can we conclude as a result of these statistics that if you're older, or I should say, if you're 55 years or older compared to 25 years or younger, you have a greater chance of dreaming in black and white? Can we say that that's a fact? And that's what the aim of this test is going to tell us. Now we already know that the results there's 5 times more results. Is that enough to conclude? Now, again, we have to assume that it's a simple random sample. You know, the samplings was carried out well. There was not much bias in the study and all that good stuff. So that's what we're going to do. And that's what this study is all about. Now, we assume that they're equal. We say, well, you know, they're equal. P1 is equal to P2. And remember, P1 is the proportion, I should say, of the adults. So 60 over 305. And P hat 2 is actually 12 over 295. So we're assuming that they're true. And there's another way to write this too. You can write this as H null. Sometimes you'll see it written as this if you subtract them. P1 minus P2 is equal to 0. So the difference, that's really what we're getting at, is the difference between them 0 or is P1 greater than P2, is the proportion of them greater. And we could write that as this. Sometimes you'll see it written in other. That's what this study is about. So the first thing you have to do is calculate the test statistic. Now, it turns out that we're not going to calculate the test statistic. We're going to use our calculator to calculate the test statistic for us. But I can show you, if you want to see the formula and you want to know how to calculate it out, I can show you, no problem. But for right now, let's do it using the calculator. So we're going to go into stats and we're actually going to conduct this test. And we're dealing with a 2 prop z test. So it's number 6. And for this test, x1 is going to be the the senior group, the 60 out of the senior group. So we're going to say that it's 60 people, 60 successes, 60 people that dream black and white out of the total 305. Now in the second group, which is the younger group, the x2 is the successes, in other words, the ones that how many actually dream in black and white. That's going to be 12. Now the population N2 is 295. Let's do 295. And we have to identify our alternative. Well, what we know is that P1 is greater than P2. So that is what we are testing. The alternative is that P1 is greater than P2. And now all you do after that is just hit calculate. Now, what did we get? We got the test statistic as 5.811. That is very significant because remember, this is the z-score on a standard normal distribution where the mean is 0 and the standard deviation is 1. That's 5 deviations positive. The p-value is 2.05 times 10 to the negative 9. That's like on the nanoscale. It's extremely tiny. All right, that's 2 parts per billion there. And now we also have p hat and p1 hat and p2 hat, the proportion of population. This is um, the p hat value. And if we keep going, let's see, and that's all we have. So the p value is very close to 0. That's like that's like 0. I mean, it's very tiny, very small. We definitely get to reject the null. We have a conclusive evidence. So first, identify the test statistic, 5.88. You always round that to 2 places because it's a z-score. The p-value rounded to 3 places, 0. What is the conclusion based on the test? Well, because the p-value is smaller than 0.01, let's just back up. We got 5.88, and the p-value is equal to 0. Yeah, what did we? I mean, it was like, yeah, 205 or whatever. This is what we're getting. The p-value is less than 0.01. So reject null and accept H1 alternative. Reject null, accept alternative. Okay? And that basically means we have enough evidence to reject the null that they are the same. We can conclude that you're more likely to dream black and white if you're older than when you were younger. And it's factual. There's again, I mean, we can't say it's factual, but it's a very strong word to say that, but it's irrefutable, especially when you have a p-value this significant. Okay, again, assuming that all the parameters and the assumptions were all made about the test, which they were. We had no reason not to believe it. It's just, this is all routine. Since the p-value is less than the significance level, so we get to reject the null. There is sufficient evidence to support the claim that the proportion of people over 55 who dream black and white is greater than the proportion for those under 25. And now to top it off, to back up our test, let's do a confidence interval, a 98% confidence interval to back up our result, because a confidence interval will let us know where the difference between these, where would that lie? Between what 2 numbers would it lie? And basically we want an interval that does not contain 0. Because if we get an interval that goes from -1 to 1, that means that the difference could potentially be 0. We know that the difference is not going to be anywhere close to 0. So they do want us to back up our results with a confidence interval. That's not going to be too difficult to do. We're just going to go back into our calculator. For chapter 7, 8, and 9, and those 10, it's all calculator. It's just autopilot. Okay, so you should be happy when you see one of those types of problems on the test, because you should be very confident that you will get it right using your technology. And if you don't got the calculator, you can use whatever statistical software that, I mean, whatever software you have. Okay, the calculator is the one that we suggested you get. Now, where do we go to get the confidence interval? Well, it's actually going to be, let's scan through this. I don't see a 2-prop-z interval test, so we do have to find that because that's what we're dealing with. All right, it's B. It's one of the last things, a 2-prop-z interval test. And I think our stats, our values are all going to still be in there. It's still loaded up. We don't have to do anything. All we have to do is change the confidence level. And I think they said at 98%, and right now we're at 95. So let's change that to 98. And then here you go, hit calculate. And look at what we have. The lower bound of our confidence interval is from 0.09 to 0.21. All we wanted to know was that 0 is not contained in this range. 0 is to the left of these numbers. So the difference between those two proportions is a positive number. That's evidence to support the claim that P2 is greater. And I will put in the two limits. They want you to round to 3 places. So 0.097 for one, and the other one is 215, 0.215. What is the conclusion that can be made? Well, because the confidence limits does not include 0, it appears that the two proportions are not equal. Because the confidence interval limits include only positive values, it appears that the proportion of people over 55 with dreaming black and white is greater than the proportion of that. All right, and there you go. An explanation for the results in that is that those over the age of 55 grew up exposed to media that was displayed in black and white. Can these results be used to verify that explanation? Not necessarily. I mean, you know, there could be a lot of factors. We don't know. I mean, for them to say that they grew up watching TV in black and white, that just seems like a stretch. Um, it could be true, but we can't say that one causes the other. We don't know what caused it, and I don't even think that matters so much in our analysis of this particular question. So I think it's more about just saying, no, the results speak to a possible difference between the proportion of people over 55 and under 25. But the results are not statistical. But the results cannot be used to verify the cause of such difference. So, all right. Let's kind of scan through. I think we're getting kind of late in the stream, so I'm going to spend some time doing some problems that we didn't get a chance to go over. So unfortunately, they don't let me scan ahead as much as I would like to, but I will say that there are videos for a large number of problems, and when you're done submitting the test, you go back into question help and it will say print the test, and it will print the test with answers. Okay. I think it would be a good idea for us to take a look at maybe a chapter 10 type of question, or something along those lines. So what I can do, I mean, I could just try to put in some numbers and just try to move on that way if they'll let me. Actually, I have to put in an answer for each one because we're getting late in the stream, and I don't. What I could do is I could just, you know what? Why don't I just submit my test, and then we can look over the rest of the questions at a little faster rate. So I'm going to hit submit. You still have 20. Okay, so I only answered 10. That's fine. Yeah, some we didn't answer at all, and I understand that. Like some we just didn't. Okay, yeah. Well, this one we didn't. Yeah, I didn't even put a choice because we're skipping that. And oh wait, why did I just? All right, so this is what you can do. You go to question here and then go to print. And then it will ask you to print this question or print the test with the correct answers. You're going to print it with the correct answers so that you can see the rest of the questions. Oh wait, did I just hit? I think I just hit print. Let's see, print. Okay. So I want all 30 questions. They actually give you a table, which is very nice. And notice at the table they give you some of the common Z-scores for different areas. Yeah, so some of the questions you'll notice are pretty similar. We did a gang of problems. I thought it was pretty helpful, but there were some we just didn't get to. I know this might be very hard for you to see on your screen right now. Like this question looks interesting. Let's see if I can copy this onto. Consider a sample of football games. Um, I can just put in my own words for that. Consider a sample of 45 football games and 30 of them were won by the home team. Okay, hold on. We actually have, I can just delete this one now. Consider a sample of 45 football games where 30 of them were won by the home team. Use a 10% significance level to test the claim that the probability that the home team wins is greater than 1/2. Identify the null in the hypothesis. All right. So they tell us that they want us to test the claim based on this data, test the claim that the proportion of oh, this is 30 out of 45. All right. Consider a sample. All right. And we also have that the significance level, the alpha, is 0.10. All right. Now, because it's greater than 0.5, we are dealing with a right-tail test. The first step would be to calculate the test statistic, the z. All right. Um, yeah. So again, you simply use the formula to calculate the test statistic. And the formula comes from here. You basically have to subtract this from the p and then divide by the critical value, whatever the critical value is. Again, the calculator will actually do this for us, so we don't even have to do it. We don't have to subtract the p from the p hat and divide by the critical value. We don't have to do that to get the test statistic. It will calculate it for us. So let's just see how would we go about solving this particular problem. Again, we're dealing with one proportion this time, so we're going to stat, go into test, and it's just a one prop z-test, number 5. P null is 0.5. The x is, what did we say, 30, and this is 45. We also know that the alternative is greater than null. Hit calculate. All right. Our test statistic is 2.23 or 2.24. Our p-value is 0.01. That's actually much less than that 10% that we have to compare it to. We got our test statistic turned out to be 2.24, and our p-value therefore is, and how do you get your p-value from that? 2.24 and up. That's your p-value. The p-value is equal to 0.0. They usually like 4 places or 3 places, so I'll just put 0.127. And now it's time to compare it to our alpha. Our alpha was 10%. Since the p-value is less than alpha, we reject null. We reject that it's 50-50 when they play at home. We get to accept the alternative. And that the alternative is that the population proportion is greater than 0.5. And then it just goes on from there. I mean, you answer the rest of the questions, you reject, and so on and so forth. All right, I think this was a good review. We will look at just one more, and that will be number 29. And for 29, let me see if I can, well, it may be really hard for me to copy it the way I want. So what I'll do is just create an image of it. Let's see if I can just paste it into the Word. And let's see if we can reshape this a little bit, right? So, well, it's because it's pasted as an image. it may be hard to do that. But this is the data. So for this, this is a chapter 10 kind of problem where we're dealing with linear regression and scatter plots and determining if there is some kind of relationship between the two variables. You do have to examine the scatter plot, and our calculator can do this for us. No one really calculates correlation out by hand. It's usually always calculated out using the calculator, and there's a lot of ways to do this in the calculator. This is actually really big time stuff when we talk about correlation, creating the line of best fit and all that good stuff. When we do that to make predictions about this, that's what this game is all about, making predictions. Okay, that's what it boils down to, and that's what artificial intelligence is about. You know, making not only guessing but guessing very precisely, better than human. Um, so that's what we're going to do here. Now, in order to do these, you do have to load up your calculator with the data. That's going to be your first step, is to put all of the values into the data. So this is problem number 27 or 29, I think it is, just before you reach the end. So that's what I'm going to do first, is I'm going to enter all the data into a list. Let me clear this list out, and I'm going to enter it in just one step at a time, okay? All right, looks like we got all those pieces of data in there. Let me double check. Yep, it looks like there was only 11, so we're going to do that now for the y. So for all the x, it really doesn't matter what's your x, what's your y. It doesn't matter in this. Okay, it didn't matter. You just put it all in. It starts to get a little sloppy. So we just put it all in. You can get the same value. 7.46. All right, let's do this. All right, we got 7.81. All right, so yeah, I mean, we have all the data. It's always a good idea to always double check, because if you're going to make a mistake, this is where it's going to come. All right? It's not because you don't know how to do it. It's just because you didn't enter it in properly. And that you don't want to let that be the reason. So you just kind of scan it carefully, make sure it's all nice and neat and tidy. And it does look pretty legit. So I'm just checking back and forth. You definitely, I mean, this is what we're testing you on as well, data entry. Right? This is a big part of where people make mistakes. And you get into a job where you gotta enter data in somewhere. You don't want to make any type of little typo or mistake, okay? It'll become an outlier or a huge mistake. Um, so it looks like the data is in properly, so that's cool. We can second quit and get back to the home screen now. All right, so now that the data's in, we could do whatever we want. Now we could actually graph this stuff. All right, let's see. If we go to second stat plot and turn on one of the plots, I'll just turn on this and turn on a scatter plot, and my X is my L1, my Y list is L2, and choose a mark. And after that, you go into zoom and then zoom stat number 9. And there it is. Oh, so it's always a good idea to examine the scatter plot to see, hey, what is this? Do we truly have a scatter plot, or is there something funny going on with the data? And to me, there's something's a little funny going on. This is not a natural scatter plot thing. This is like some kind of legit trend that we have, and then some outlier happens, see? And that's either a typo or it was intentional. Now, if we hit trace, we can actually skip around to each point. And I can even see this point is x13 corresponds to 12.74. So if I go back to my chart, there is a point 13 that corresponds to 1274. So that is legit. That is right. So we graphed it, we inspected it. There is some kind of trend happening. That's fine. So the first question is, how do you get your R, your correlation coefficient? All right, we know it's going to be positive because the data is trending upward, and we know it's going to be pretty strong because it's in a linear formation. So we go into stat, we go over to, there's a lot of ways to do this. There's a test that we can run. Some people do just calc and go to linear regression and choose number 4, plug in L1, L2, and then just hit calculate. Now notice, look at this. I didn't get the R because I turned off my diagnostics. I have to turn it back on. I did that deliberately. We saw this earlier. Stat diagnostics is turned off. You have to turn it on. Activate that. Now another way, if you get lost and you don't know where something is, there's a catalog in your calculator, and it lists every possible command in alphabetical order, in alpha order. So if you go to second catalog, there it is. And if I'm looking for diagnostics, that starts with a D. I can actually go to alpha D. Just hit D, it jumps down to the D's, and I can just go all the way down until I see diagnostic. Diagnostic on, turn it on. I found the command, hit it. It's now done. It's on. And now when I do back my second entry, well, let's see if we can recall that other command. My linear regression, L1, L2, they're not even going to accept that. So let me just go back into it. Stat, calc, linear regression number 4, choose it. Frequency, I don't need it. You could just choose 1 or just leave it blank because we don't have a frequency distribution table. And we're not going to store our regression equation in any variable. I could put it in Y1 if I wanted to graph it, but I don't even think they're going to ask you to do that. So hit calc. Now I have my R. I even have R squared, which is the percent of variation between the two variables. But R is the one. It's positive and it is very close to 1. It's 0.81. So that lets us know that there is a strong correlation. Now, there's actually another way to do this. And if you go into stat, but this time conduct a test, you actually carry out a linear regression test. It's one of the very last things, F. Just leave it all like that. You can actually change this to not equal and just hit calc. It's going to give you your R as well. Okay, 0.81. Now, it also gives us a lot more stuff like the p-value. Look how significant, how small that is. That basically means that there is definitely a correlation. All right. That is pretty much all you need to know about Chapter 10. Also, I mean, you do have to be able to interpret scatter plots and things like that, but for the most part, I think we're going to start to shut down the review at this particular point. I know it's getting kind of long, but I do encourage you to spend some time and review this, spend some time on this. And also, I'm going to be online quite a bit, and I will be monitoring the online a lot and just looking for questions that may be coming in. And it could be questions from the past. I mean, chapter 6, 7, 8, 9 stuff, chapter 10 stuff. I think we did a problem from every section. I even mentioned some problems that you don't really have to worry about. Let's take a peek at problems 15 and then 18 really fast. Um, so let me make sure that 15 starts right there. It's just, okay. So 15, let's take a peek at 15 there. Refer to the company data. So they give us the data. It looks like they gave us an interval, a confidence interval, the mean of the confidence interval, the standard deviation, and they gave us the sample size. What is the number of degrees of freedom that should be used for finding the critical value, T alpha over 2? Now, the degrees of freedom is going to be one less than the number. It's just kind of what happened was that they proved mathematically that if you subtract 1 from the sample size, your answer is going to come out better, closer to the actual thing. And so for that reason, this is all we're all trying to estimate the population parameters. We don't know the real population. We have sample data. So when you have sample data and you want your estimations to be very accurate and you want them to resemble the true population, we will take a degree of freedom from that sample size. And what you do is you just subtract it by 1. Now, if we were dealing with 2 samples, then you'd have to subtract each sample by 1. But whenever you have 1 sample, you take 1 away from it. What is the number of degrees of freedom that should be used? So the degrees of freedom will be 49. We got that from 50 minus 1. Find the critical value T alpha over 2 corresponding to a 95% confidence level. All right, now some people may not have this command on their calculator because you actually got to do an inverse T. And we're corresponding to 95% confidence level. That's the innermost 95%. Let's look at this pictorially for a second. Innermost 95%, which basically means we have 2.5 here, and we have 2.5 here. I know this is a little, just work with me, okay? Just work with me for a second. We need to find this guy. And we're dealing with a t distribution, which is not even normal. It's an approximation of a normal. So we got to find this number, and we know that the area to the left is going to be 95 plus the 2.5, so 97.5%, which is 0.975, the area to the left. So what I'm going to do is use inverse T now. I may not even have this type of problem on the test because some people might not have inverse T. And if you don't have inverse T, then, Now, we go to second distribute, and inverse t should be under inverse norm. If you're working with an 81, they just don't have inverse t, but there is a workaround. There's a way to program your calculator to have inverse t. So inverse t needs the area to the left and then the degrees of freedom that you're using. So I'm doing 0.975, and then the degrees of freedom is 49. And look at what I got. I got 2.01, and that's what they got for their answer. 2.01 for the critical value. And now we have to make a statement. What does that mean? Give a brief general description of the number of degrees of freedom. Well, yeah, I mean, let me see, looks like it's kind of cut off. I don't know why it's cut off. That's kind of odd, but the number of degrees of freedom for collection of sample data is the number of sample values that can vary after a certain thing. So they just cut it off, so you can't really read it all, but that would have been the answer. Okay, let's look at another one real quick, like 18. Find the area of the shaded region. The graph to the right depicts IQ scores, and those scores are normally distributed with a mean of 100 and a standard deviation of 15. So you're going to do a normal CDF. Your lower bound is 84, and your upper bound is unbounded. So you're just going to go into stat, actually not stat, second distribute, normal CDF. Your lower bound, again, 84. Upper bound, some large number. Your mean is 100 because we're talking about IQ scores, and the standard deviation of IQ scores is 15. So we got 0.8569. 0.8569 is good. Yeah. So that's how you work that one out. Yeah, no problem. All right. So hopefully this was helpful, guys. I really appreciate you guys hanging in there. The stream was pretty long, I thought, but you know, sometimes we do have to spend some time on this. And if there's other questions that pop up about this, reach out to me and I can either make a video about it or kind of walk you through it. All right? All right. Thanks for watching, guys. We are going to shut it down. Be in touch soon.